Hi everyone, I'm Abhishek, I'm from Purdue, and this is Sanchit from NYU. And as PhD students, we deal with a lot of research prototypes. Ours are other students and AI-generated ones now. And the problem is they never actually run. And it's always some sort of an SO file that's missing or some CUDA mismatch or some native dependency that's just supposed to be there. And based on the talk I attended yesterday, this is not just a grad student running bad code thing. Looks like everyone runs into this problem all the time. So today we're going to dig into what's hiding inside your Python build, why it's not always reproducible, why your requirements file isn't always giving you the whole picture of what's in your software, and what we're building to make it more visible. So this is the example I'm talking about. So whoever tried to install like VLLM or any ML inference library, so this is what happens. You see that pip says it successfully installed something. You run pip freeze. You see that it's there. Everything looks perfect, but then when you actually try to import it, you see that there's an import error saying that it can't find some shared object. And pip told you that everything was fine, but pip actually lied. Not exactly lying, but pip has no idea that VLLM needs a specific version of CUDA runtime library that was compiled into the wheel. And this is from a real GitHub issue, and there's this something that a lot of people ran into. And it's not just an ML library thing. Here's cryptography, probably the most popular security package. And it's the same story. Pip installs it, and when you try to use it, you see a libSSL error. So this is because, again, the cryptography library bundles Rust code and links against OpenSSL at compile time. So pip metadata just tells you cryptography a certain version. It says nothing about which OpenSSL version is bundled in, and whether your system has all of this, and if it's compatible. So it's two different packages, and the same fundamental problem. It's that the crucial stuff is not visible to pip. And zooming out a bit, so what's actually inside the software that you consume? On the left, you see that there's a manifest file, your requirements, your log file, and it knows about the packages you explicitly asked for. The reality is that there's still a black box there, which is way more complex. Your software depends on the shared library, like libSSL, libcrypto, libc. So these get pulled during the build, and some of these have known CVEs. And this XKCD is something that we've all seen probably. So a lot of modern software probably runs on that one project maintained by one guy from 2003. And the point is that your manifest captures maybe the top layer, but everything below is invisible. And this just isn't an edge case which is limited to those libraries. If you look at this Docker file, this is a standard way of deploying Python apps. You apt install a bunch of C libraries, build tools, and then you pip install the project that you want to run. So those apt packages, again, pip has no idea they exist. They won't show up in your pip freeze, and they won't show up on your SBOM now. So looking at this table, there's a lot more of these happening when you bundle Rust or C code with your projects. So right now it might feel like a developer experience problem, but these hidden dependencies are not just inconvenient, they're an attack surface. SolarWinds happened because attackers compromised a build process and nobody could see what changed. XeUtils again was poison, like native libraries that was slipped in because nobody was tracking it. So every one of these libraries at some point had a CV, and none of them show up on your requirements. So that's the problems SBOMs were designed to solve. So what is an SBOM? A brief overview is it's software bill of materials. It's a machine-readable inventory of everything that's used in your software. So on the left, you see what pip freeze tells you. It's a name, a version, but there is no other context there. On the right is what an SBOM actually has. So for every component, you have information on who supplied it, a cryptographic hash so that you can verify if it has been tampered with, the exact download URL so you know where it came from, the license information, the full dependency tree. And the second entry is the native library stuff that pip can't see, and SBOM is supposed to capture that information. There are two main formats, CycloneDX, SPDX, but I won't be going into that today because the format doesn't matter for today's talk. What matters is what the data in there is actually, if the data in there is actually accurate. And SBOMs in general are not optional anymore. Both the US and the EU governments are pushing for it. So it's a requirement for any software that you ship. So to show the utility of SBOMs, when the Log4 shell incident happened, the exploitations went from 40,000 to almost 1 million in 3 days. And organizations were asking if, are they vulnerable to Log4j? Nobody knew. And Log4j was buried often in like three dependency levels underneath. And teams spend days like grepping for any signatures of Log4j's presence in their code bases, and they're asking vendors regularly if they know of any incidents where it happened. So SBOMs solve this issue. You just query if you have Log4j, and then it tells you what services has it, or which version, if it's vulnerable. So you go from days of solving it to just minutes of finding the solution there. So that's the promise of SBOMs, but SBOMs turn any investigation into a database lookup. But the important part of the promise is that it only works if the data is accurate and complete. And we saw the case with pip freeze. So what if the SBOM is wrong? So what if it's missing things? So here's the question you should be asking about when you receive an SBOM. So how was it generated? What tool and at what point in the supply chain pipeline was it generated? What information did it capture? Was it just the manifest, or was it actual build output? And is this information accurate? Are the versions that were pointed out are correct? And finally, are the hashes that it shows you actually correct? And can you verify that it wasn't tampered with? The spoiler is that most SBOMs generated today, they don't really answer this question too well. So let me show you how these work right now. So here's a typical Python project. You have requirements, you have declared dependencies, you got frozen requirements. So the frozen requirements is supposed to pin the exact versions, but in this case it is stale. So you've got the source code, and if you run any of the current tools available right now, you see that there's two manifest files now. The frozen requirements on the left have the exact pin versions. So these are the requirements, NumPy and GRP, CIO versions, along with the transitive dependencies. And the requirements on the right has just ranges. So it doesn't pin on any particular version. So it has two different views of the same project, and they already disagree. So here's the problems. The SBOM tools at these files, they can't process this information. They see the ranges, and what version of requests it actually uses, or what version of NumPy it can't actually deduce. So it falls back to using the frozen requirements. It takes the pinned versions and produces the SBOM from there. The SBOM is confident that it uses that version of requests, NumPy, and all the 5 packages that you see there. But it is, in this case, it is reporting old versions that might not actually have been installed when you do pip install. So the SBOM looks complete, but it's not actually complete. But this is not a bug in the tool. Most SBOMs are either generated before or after the build process. So if it's generated before, you're reading manifest files. So you miss everything that was already present in the build environment, and you're missing artifacts that are generated during the build. So this is like the Docker setup example I was showing you earlier about, where you're setting up libraries and then installing the project. And if you do it after, you are scanning the output. So you're missing transitive dependencies that were used during the build and discarded. And someone could have tampered with the artifacts before the build finished, and the scan starts running. So neither approach actually watches the build. So that's the gap we are trying to address. And this, okay, I think you skipped one slide. Okay, we might have skipped one slide there. So this is a problem that we see we analyzed Docker Hub, and we saw that this is a problem which is common in even Docker Hub. We saw that we ran this analysis on 5,000 images, and we saw that 30% of the files are actually untracked, So these are not known by the package manager. So if these are not known to the package manager, these end up not being in your SBOM. And we see the same behavior in 3 other platforms. We saw the same analysis on, we did the same analysis on Maven Central, Jenkins plugins, and VS Code extensions. The patterns are different. In Java, it's because you're shading or you're nesting. In JavaScript, it's because of bundling or minification. The result is the same. The packages exist inside your artifact, but they're totally invisible to any metadata-based scans. So this is often a systemic problem, not like accidental thing. So shading in Java exists because you want to deal with version conflicts. So it's a deliberate choice. The side effect is that the downstream consumers have no visibility into what's actually in your artifact. So developers knowing can embed and maintain these dependencies, but the consumer they can't really access the information that was in your software. So if someone doesn't want to, even if someone does want to hide something, these channels make it easy for them to actually do any malicious activity. This is from an ongoing research project. I'm happy to talk more about it after the talk. And moreover, even if manifest files exist and are up to date, they don't capture everything you need. They don't always tell you the resolved versions of the dependencies. They don't tell you which registry was used. Did it come from PyPI or some internal mirror or from somewhere that you didn't expect? And they don't tell you about any rogue processes or unwanted network calls during your build. So all of this is crucial for your security, and none of this is actually in your SBOM. So putting it all together, here's the software supply chain. There's source code, then you build, package, and deliver. So attackers can compromise every stage. They can inject malicious code in your version control system. They can hack the compiler like SolarWinds. You can forge SBOMs, and the testing can be incomplete or totally missing. And the SBOM is usually generated off to the side. It's from the packaging stage, typically, with no visibility into what actually happened during the build. So all of these red lines are real attacks. These have happened in the wild. So SBOMs is supposed to be a source of truth. So if it's disconnected from the process that is supposed to describe it, it will not be accurate. So we propose a fix to this. First, we move the SBOM generation process to the build time, not before or after, but during the build. And next, we capture all the relevant data from the build, every file that was accessed, every network call that's made, and every process that is spawned. And then we make this information cryptographically secure and verifiable, so nobody can tamper with the data. So this is what our tool, SBOM, does. So this is the SBOM pipeline. The first step is we observe the build. So we actually watch what happens when pip install runs, when test execute, or when the wheel gets packaged. And the next one is we record attestations. So this is structured, signed records of every action. And then we compute package information from what was actually observed. So we resolve the files back to packages, match the hashes, identify versions, and then we have a complete inventory, and the output is an SBOM. So this is not just what the manifest file claims, but this is what you saw during the build. Now I'll hand it over to Sanchit. He'll explain how this works.
OK, so when we look at the steps that, when we look at the steps that we need to generate an SBOM with SBOMit, most of it might be obvious to you, but not a lot of people may be familiar with what we mean by attestations when we say that we record attestations. So I'll briefly be talking about the what's, the whens, and hows of witness, in toto, and attestations. I'll be using these 3 terms to mean the same thing for the purposes of this talk. They are slightly different in reality, and I would be happy to chat about that later, but for the purposes of this talk, when we say attestations, we mean attestations generated using witness, which is a tool, and in toto, which is a spec. So what this actually does is that it actually monitors the build that you had. So it will look at the processes that were spawned, what were the files that were accessed when you ran Python build or cargo release, cargo build -- release, or whatever your pipeline might look like. It also looks at the Git commits that were present present in the directory that you're building. It looks at the environment variables. It also looks at the network calls that these processes might be making. What it gives you at the end is this attestation, which has these different plugin. It has like a plugin architecture. So for example, if you want to have a very specific type of attestation that you want to record, maybe you have a Docker build and you want Docker-related information there. You might have an AWS build. You might care about the Git commits. You might care about the environment variables. You can configure what you actually want to capture, what you think the attack surfaces might be, and it will give you information about what actually happened. And each of these attestations is essentially independent of one another, so you can kind of like configure them as you go. So if you want to imagine that you're a detective and you're like trying to get to the bottom of what happened during your build, like the attestations are kind of like photographic evidence of what happened. Like they tell you exactly what happened, when it happened, what files were touched, what it was doing there, and it gives you that in a parsable format for you to consume later. When it runs is actually what Abhishek has been talking about quite a bit. Like we want to actually observe the build. So witness essentially wraps around your existing pipeline for the build that you might have. This might be a really complicated shell script. This might be a single command. Whatever you're running, you can just wrap it around, witness run with whatever configs you want to, and it will essentially monitor what happens during the build. And how it does this is essentially, for the purposes of this talk, we'll be talking a lot about the files that are opened and the processes that are spawned, and a little bit about the network calls that are being made. So if we just look at this, it currently uses ptrace to monitor all the processes that were spawned. It will look at the syscalls that were made, any syscalls that are related to opening a file or execing something. And for network calls, which has experimental support right now, it uses eBPF to have like a transparent MITM proxy, so it can actually also read HTTPS requests. So you can have like a hash of what the request was, what the response was. And as Abhishek mentioned, like this is also quite a critical attack vector when it comes to supply chain attacks, because suppose you only want to fetch from like an internal, you only want to fetch from an internal registry that you have for your project, but that call went to a server that you did not expect, or maybe you even leaked out to PyPI for whatever reason. Like you having this information of where these calls came from, what the hashes were, are really important when you're trying to do a deep dive into how secure your final build artifact is. So I think we should have probably started with this earlier, but the it at the end of SBOM stands for in toto. So our main idea is that we take in SBOM tools like Sift and Trivy, which do like software composition analysis to give you a detailed tree of dependencies of what is actually going into this project. We enrich it with in toto attestations, which gives you the actual data of what was accessed. Like, were these files ever present? Like, were these files ever touched? What were the files that SCA did not report but were actually touched? For example, the shared object files that are often required for builds. And what we have at the end is like an SBOM enriched SBOM, which is supposed to give you an entire picture of what actually, like what is the software that you shipped, and what you're vulnerable to, and what you're not vulnerable to. So for instance, on the left we have something that a non-enriched SBOM would give you versus what SBOM would give you. And in this very particular example, reading the manifest file tells you that there's this version of request, this version of NumPy, this version of cardet. But when we actually run in toto against it and we actually see what were the things that were being pulled, we see that these packages are not correctly versioned, and also there are a lot of shared object files that are being touched, which may or may not be relevant for your case. So we have false negatives and false positives, and also just missing information when it comes to a lot of these builds. So I will quickly run through a simple example. Let me minimize this. I'll quickly run through like a simple example where we're running it against we're running it against our JSON, which uses Matalan, so it has some Rust dependencies. But like it builds you a Python wheel. So I'll just be running you through what it actually looks like to run witness, what it actually gives you, and what the enriched SBOM is telling you about the SBOM that traditional tools like Swift or Trivi might have missed because they do not have information about this. So I'm not sure if this is visible. I'll try to zoom in further. But yeah, so in a sense, everything after the 2 dashes, which is like the shell script with material build release strip, that is the actual build. That is how you actually build our JSON, and everything before it is essentially like what is your signing key and what options you want to run it with. In this case, we are running it with the command run trace, the command run attestor, which will essentially give us a list of the files that were actually opened, and it will output it into a JSON. This should not take that long, but essentially, like, your build process does not actually change. Like, it goes through all the steps that your build regularly would. It's just that Witness now has the ability to track what is happening during that build. So for like every time cargo or Maturin are accessing a file or writing to a file, we will have that information in the final attestation. So yeah, these are the various attestors that were run. Command run was what we specified, and there are a lot of attestors that are run by default. For example, the product attestor, and I think Git and material run before the build command runs. And quickly going through what this would look like. So this essentially is what Witness gives you. It's a in toto specification, in toto compliance specification for an attestation, so it will tell you what attestations were run. And later, since for our purposes this is important, it gives you what processes were run, what was the command that was run, and what were the files that were accessed, what was the hash of these files. So a lot of these times, these files are just going to be shared library objects, or these might be caches, or these might be actual Python, these might be like actual Python or cargo packages. And in essence, this is a photographic picture of what happened during your build. Like, these were the files that were accessed. This was the state of the environment. This was this is the state of the Git. This is the state of the Git tree when you run it. And we can use that information and run it against SBOM. So what we're doing here is we're asking SBOM to generate us an enriched SBOM, and we're providing it with the input file, or JSON.json is it is the attestation that we just generated. We're going to be using Swift as a catalog here so that it can use the information Swift has about transitive dependencies and dependency trees, and also for us to compare our output to an existing tool. It'll output it to a file, and the show enrichment flag is essentially just like it just pretty prints this. So in this case, when you do SCA and you use Swift, there was a cargo package that was missed by it. And more importantly, there's also a bunch of added files that a regular SBOM never talks about. These files might be relevant for your build. These files definitely need much more analysis of whether these are just caches that you can ignore or whether these are actually shared library objects that are meaningfully packaged and bundled in with your software. But in a sense, that is how you use it. So it's a very simple step where you can just wrap it around witness and have an enriched SBOM and have more information to go about it. So now coming to the takeaways and the conclusions that we can draw from it is that enriched SBOMs try to fulfill the promise that a regular SBOM was supposed to give to us, which is that we need to have information about what we're packaging, we need it to be accurate, we need it to be verifiable, and in toto is a step towards doing that. And also, since in toto uses OS and kernel level mechanisms to actually detect what was happening, you don't need to build a very specific wrapper around Python and then NPM and then cargo and then Go. It's just using very core OS primitives to essentially give you that information. And when it comes to building trustworthy software, we need to not think of SBOMs as just a compliance tool that the government asks you to fill up so that you can go sell your software. It is also supposed to be like an active part of your arsenal when you fight against supply chain vulnerabilities. And SBOM, it helps you towards that path. It is secure by design. You don't need to trust 1,000 different people about whether your SBOM is correct or not. Even if your build pipeline is compromised, you will actually have information about what actually happened during your build. And because you have a better SBOM, you have fast vulnerability tracking. So for the call of actions, SBOMit and Witness are all open source tools. They're available for you to use right now. We would highly encourage you to try it on your Python projects, especially if they're combining multiple languages, if they have something funky going on, run it against SBOMit, see what SCA is missing for you. We would also want you to do deeper into what you're actually packaging. If you unzip your wheel files, look at what files are there, see if they belong in an SBOM and whether your SBOM tool reported them as being in the SBOM. PEP 770 is already a standard that was adopted by the Python committee, and I think there are around 300 packages that already use it, and we would highly appreciate everyone using that whenever they ship code, because it helps with much easier detection of packages that we use in your SBOM. And more importantly, since this is an open source project, this is supported by the OpenSSF, so we would highly encourage you to come help us improve. If you see something off here, or if you know that these files should mean this thing, but your tool is not actually talking about it, please come talk to us. We have meetings every Wednesday on 11 a.m. EST where we discuss where we want to take this project, how best we can contribute to it. Both Witness is a CNCF project. You can also you're more than welcome to come and contribute to it, try to add new attesters, try to make it faster, try to make it more secure. And SBOMit, again, is open source, and here's the QR code to join the OpenSSF Slack for the SBOMit channel. Thank you, that's all. We have, I think, a minute and a half for any questions that people might have.
So I have a question. Thank you for the presentation. I appreciate what your tool is accomplishing. My question is more around SBOMs in general. If I have to support multiple Python versions, I may be importing different libraries for different versions of Python. And I don't quite understand how I can illustrate that with an SBOM. Like everything is in my UV log file, even my whole tool chain is I have in there, so I can even see what versions of PyTest and everything else I'm using in there. So I'm confused how I can leverage SBOMs where I have to support multiple things and why I'm not just extracting that data from my UV log file.
Yeah. So as we mentioned, SBOM gives you more information than a typical manifest file would. For example, we need to know much more. When SBOMs are typically required by various governments or organizations, they also look at who is supplying them or what the licenses are. For example, maybe you're using the wrong sort of license for your open source project. That is something that SBOMs help you do as well, apart from the security aspect of it. If you want to add anything more.
I'm not really familiar with UV. Maybe the manifest file looks a bit different, but I think this is something for us to look into. I'm not really familiar with UV.
I think it's just fast version of that.
Okay.
Also it does a lot of things differently. I don't want to.
I guess to clarify, I guess in general, a log file where all my versions are pinned, it doesn't have all the information in the SBOM, but that could be a reference point on what versions.
Yeah, so traditional SCA tools actually use that. Your log files are actually important for SIFT or Trivy or any SBOM tools to know about what happens in there. So we're not asking you to abandon them. They build upon them. So for example, your log file might also give you information about what is the dependency tree. Is this package a direct or an indirect dependency, which just observing a process would not tell you anything about. So it's more of using log files to build an SBOM, which will have your information in a much more workable fashion and something that passes all the requirements that your government or your organization might have.